Hi friends, in this video we are going to speak about the time period of a simple pendulum. And before speaking about time period of a simple pendulum, what is a simple pendulum? Here we can see a simple pendulum, that is a string attached to a mass which is oscillating. It is called as a simple pendulum. What is time period of a simple pendulum? Time period of the simple pendulum is the time taken for one complete oscillation. That is, if the pendulum is over here, the time taken for this pendulum to reach over here and come back to that same position, it is the time period. We are going to derive a mathematical expression for time period of a simple pendulum. For that, let's draw a simple pendulum. That is, let this be a ceiling over which there is a lengthy string over which a mass m is attached. This is our simple pendulum. Let the length of the simple pendulum be L. Then we are applying a force in this direction and the pendulum is displaced to a position over here. Let me draw the displaced position of pendulum like this. M mass is displaced over here and it is displaced by an angle theta. The displacement that it is having is, let's call it as x. X is the displacement, theta is the angular displacement. Then at this position the pendulum will experience a gravitational force which is acting vertically downwards. The gravitational force over here, it should be mg, and this mg gravitational force, it could be resolved into one component like this and one component like this. That is, we are resolving the gravitational force into one component in the direction of the string and one component perpendicular to it. Then, as we all know, if we are having parallel lines like this, if there is a line intersecting the parallel lines like this, these two angles are equal. By using this concept, we could say if this angle is theta, this angle should be theta. Since this is mg and this is theta, we could say this is mg cos theta. The component which is near to angle is its cos component, and this component we could say it is mg sin theta. Then the necessary condition for a substance to execute simple harmonic motion is there should be a restoring force in the opposite direction of the applied force. And let me write the applied force as, since we are trying to move this pendulum like this, or if we are moving this pendulum by a displacement x, the applied force is ma, where m is mass, a is acceleration. Then as a result of this applied force, there is a restoring force acting which is in the opposite direction of displacement. The restoring force that is acting in the opposite direction of displacement, you could clearly see it is mg sin theta. Therefore, I am writing the restoring forces mg sin theta. I am putting it as minus mg sin theta because the negative sign is indicating that the restoring force is in the opposite direction of displacement. It is in the opposite direction of displacement. And we could say At equilibrium position, the applied force should be equal to restoring force. Applied force should be equal to restoring force. Then we could write applied forces MA is equal to restoring forces minus mg sin theta. We could write like this. And from this, we could cancel this m and m, and we could write A equal to minus g sin theta. Then, from our earlier class and all, we know the acceleration is, we have learned the acceleration as acceleration is equal to d square x by dt square. This is the expression for acceleration. We have learned acceleration as d square x by dt square, where x is displacement. Therefore, I could substitute for acceleration over here. Then I could write d square x by dt square is equal to minus g sin theta. Then, in the simplified derivation of time period, let me say, consider the angle as very small. If the angle is very small, we could say sine of angle is approximately equal to angle. That is, I am giving an approximation over here. If theta is very small, I could write sine theta approximately equal to theta. We could write like this. If theta is very small, sine theta is approximately equal to theta. Therefore, in this case also, we are displacing the pendulum with a very small angle. If it is very small, sine theta could be approximated to theta. As a result, I could write d square x by dt square is equal to minus g theta. And we have learned in our previous classes and all, in our earlier classes and all, a relation between angle, arc and radius. Let this be the angle and this be the arc and this is the radius. We know angle is equal to arc by radius. We have learned an equation like this, angle is equal to arc by radius. And if I am using the concept for this angle, that is this angle over here, the angle is equal to arc. Arc length is x. Radius is L. Therefore, I could write d square x by dt square is equal to minus g into angle is equal to arc by radius, that is x by L. We could write like this. Then, if we are rearranging, let me write the equation over here. If I am taking this minus g into x by L to this side, we could write d square x by dt square minus will become plus g by L x is equal to 0. Now we are having a second order differential equation. Now this is a second order differential equation, and as we have learned, the standard equation of simple harmonic motion is, that is the second order differential equation of SHM is d square x by dt square plus omega square x is equal to 0. This is the standard equation for simple harmonic motion. And the equation that we have obtained over here is like the standard equation of simple harmonic motion. The only difference is, instead of this omega square, we are having g by L. Therefore, we could conclude that since this is resembling the standard equation of simple harmonic motion, the pendulum is executing a simple harmonic motion in which the omega square value is g by L. Therefore, I could write omega is equal to root of g by L. And we have learned omega is having a connection with time period. The connection with angular velocity and time period is omega equal to 2 pi by t. Therefore, omega can be represented as 2 pi by t is equal to root of g by L. Then I could write t by 2 pi as reciprocal, that is root of L by g. T is equal to 2 pi root of L by g. This is the mathematical expression for time period of a simple pendulum. What is T? T is the time period of the simple pendulum, time taken for one complete oscillation. What is L? L is the length of the simple pendulum. G, it is the acceleration due to gravity. Since we have derived the expression for time period, as we know, frequency is the reciprocal of time period. Therefore, the expression for frequency will be 1 by 2 pi root of g by L. Okay. From the expression for time period of simple pendulum, it is clear that time period is depending on the length of the simple pendulum and acceleration due to gravity. Can you see m inside this equation for time period? No. Therefore, time period is independent of mass of the pendulum. Whether the pendulum is having a very small mass or a very large mass, it doesn't matter in the time period of the simple pendulum. It only depends on the length of the simple pendulum and acceleration due to gravity. Hope this is clear.